this webinar is part of the IEEE PES Young Professionals webinar series. I am Aaron St. Ledger. I'm an associate professor at the United States Military Academy at West Point and also the chair of the PES Young Professionals Committee. With John McDonald here today. He's an excellent speaker. He has a lot of industry experience in standards making and within IEEE PES Society and Seeker as well. His current position is he's a Director of Technical Strategy and Policy Development at GE Digital Energy. A little bit of his education background. He received a bachelor's and master's degree in electrical engineering, concentrating in power engineering from Purdue University. And he also attended University of California, Berkeley, and received an MBA in finance from there. He's been extremely active in IEEE throughout his career. He's a fellow and has been awarded quite a few awards, to include the IEEE Millennium Medal in 2000, and also Excellence in Power Distribution Engineering Award in 2002, are two of the big ones that caught my eye. He's actually a past president of PES, also past IEEE Division 7 Director, and very active currently in smart grid standards development. And he also teaches smart grid courses at Georgia Institute of Technology and also a course for GE as well. And with that, I want to leave it to John to get going.
Yeah, thanks to Aaron. Thanks to the Young Professionals activities within IEEE Power and Energy Society. It's something that has always been very important to me and everything that I've done. And so I appreciate the opportunity to speak to all of you today. As Aaron said, I've actually been a member of IEEE and the Power and Energy Society for 43 years, and very active teaching, writing papers, a lot of leadership positions, and also, as Aaron said, in the standards development area. I got my start in the Substations Committee as a working group chair, then a subcommittee chair, and then I chaired the entire Substations Committee. And we put together a book, which is in its third edition now, called Electric Power Substations Engineering. It has 22 chapters on all aspects of substations, and also was on the IEEE Standards Association Board of Governors. So I want to take the experience I have, and both within GE and industry, as well as with leadership activities and standards and things, and bringing that all together into the topic today, which is smart grid. And truthfully, the term smart grid, we all feel, many of us feel, is overused. It's been an umbrella term, kind of a catch-all for everything that we talk about. The term that we're using more frequently now is grid modernization. But within that context, I want to talk about concepts, solutions, standards and the importance of standards, examples of recent deployments, and then lessons learned from the deployments. And I'll finish up with highlights of an article I wrote for IEEE Potentials magazine, the magazine that the IEEE student members received back in 2011 on the first job that I had in 1974 out of graduate school at Purdue, okay, and what I learned from that job. So the first thing is the work that all of us do and the decisions we make really need to be in the context of what's happening in the world around us. So what are the key industry societal trends? If we aren't familiar with these, in other words, if we stay in our companies, focus totally internally within the company, never get out in industry, attend like PES meetings, conferences, have some external focus, I guarantee you that the decisions that we all make will be suboptimal, right? Because they'll be made with only internal information, only within our company and what the company is doing, and not in the context of the world around us. So here's six items that are very, very important. One is that, and we'll talk more about this, is transitioning from devices and systems to holistic solutions. A device like a microprocessor-based device, key component today in everything that we do. The industry term, it's actually a standard IEEE term, is Intelligent Electronic Device, or IED, and that has two parts to the definition. One is it has internal processing capability, but the other one is it has two-way communications capability. So these devices can be part of a greater network, an integrated solution. And I'll show you examples of solutions because that's really the trend today. And from a business point of view, the integrated solution brings more value to the customer than just the device or the system itself. So we'll see examples of devices and systems which are more like traditional products versus a solution which meets the business needs of the customer, and it's a set of technology components integrated together to interoperate. Okay? And the word holistic is important from the sense of within our organizations, when you have a need and you go out to, say, purchase technology or look for a solution, rather than just looking at our own needs within our own groups, within our organizations, we should really think about removing the barriers, removing the walls between our siloed groups, and reaching out holistically across our organization and say, you know, I'm in the metering group, for instance, and I'm buying two-way communications to blanket my service area to support my smart metering that I'm putting in. What I should do is reach out to the distribution engineering group at the utility and say, hey, when you do distribution automation, you're going to need the same kind of a communication infrastructure, wireless, two-way, reliable, that blankets the entire service area. Why don't we write one request for proposal, go out for bid, combine the function requirements in one document, and choose a technology that satisfies both of our needs. So that's looking at things holistically. And the benefit to the organization is you make one investment, the business case is a lot stronger because you're providing benefits to more than just one group. Okay? Second is, instead of just technology, we need to pay a lot of attention to standards and policy. Okay? With technology, as I talked about solutions, integrated set of components. Components could be from different vendors. The only hope we have of those being able to talk to each other is if they comply with the same standard or sets of standards for, let's say, communications, for exchanging of information, right? And so standards-based technology is a must. And then policy is the incentive for the customer to invest in our technology. So again, we could have the best technology that's standards-based, but if policy isn't incentivizing the customer to invest in our technology, no matter how good it is, we won't be successful in sales. Okay, so policy is key, and it's the strongest driver for customers to spend money. Okay. Third is flexibility. So some of the new things from a cultural point of view that are important here, trends are distributed intelligence. Our architectures have been very much of centralized architecture where all the information from the field is communicated up to the control center. Operators in the control center analyze it, decide what to do, and then control commands are sent down to the field equipment. What we're advocating here is let's distribute the intelligence. For instance, we can put applications and decision making at the substation level, downstream of the control center, and do analysis and decision making and control at that level, and then report upstream after the fact in terms of what happened. And so if we distribute the intelligence and we close the loop on software applications, take the human out of the loop, so once we test the logic, let the logic do its thing, we truly could have a self-healing grid. When a disturbance occurs, it could automatically be detected, isolated, and service restored upstream and downstream of that faulted segment, all automatically, which gives us self-healing capability and the ability to reconfigure the system automatically, okay, with logic. So these are key, and what this does is, in the fourth bullet here, it gives us a system that's much more resilient to stress. Stress could be something like Hurricane Sandy, or an extreme, some extreme weather event that really stresses the grid. And then the question is, when it's finished, how many outages are there? What's the extent of damage, and really how resilient was the grid to that stress that was put on it? So we make a lot of decisions today based on the equipment that we choose, the architecture that we decide to implement, which is how reliable, how much redundancy have we built in, and the end result of that is some amount of resiliency. The fifth item is big data, managing the increasing amounts of data, using the cloud and the security associated with that, but also using social media. And I'll talk more about that in a future slide. And then lastly is bringing together the information technology and the operations technology groups within the utility. So on the next slide here, when we talk about concepts, to me, one of the biggest challenges here is just this last point on the trend slide is the integration of the electrical side of the utility, which we call OT, operations, and the information side, or IT, so that important information that we have on the operations side, we can bring it across the firewalls and onto the corporate network. And it's easier access then by a number of different groups in the utility, like asset management, power quality, maintenance, to be able to access that information. So comprehensive solutions that improve the reliability and the performance, the productivity, deliver increases in energy efficiencies. We also look at the environmental impacts of what we do, and part of the business case is usually how many millions of tons of carbon dioxide will be prevented, from being released to the atmosphere when we implement this new smart grid application. These last two bullets are very new to us. First one is empowering consumers to manage their energy usage and save money without compromising their lifestyle. So this is engaging consumers, understanding consumers by consumer segmentation, giving them the tools and the education to manage their energy use. And then lastly is integration of renewables into the grid and optimizing that. It presents challenges for us from an operational point of view because of the intermittency and the inability to accurately forecast what's going to happen in the future. So we've been adding intelligence to the grid for some time, and what we've been doing I call old grid, and it's highlighted in gray, and what we're doing new with smart grid is in light green. So you can see on the bottom, voltage control is half shaded. So we've been doing voltage control for a long time, because when we control voltage, that's directly proportional to load. So if I lower the voltage, I lower the load. It's a very effective way to do load management. What we're doing today, though, is we're integrating voltage control with reactive power control that we call integrated volt bar control, IVVC. Then we're integrating renewables both in the transmission, distribution, and customer site, right, with, say, rooftop solar panels. I want to talk more about residential rooftop solar panels here in a little bit and the impact that has on the grid. The second level here, sensors, is half shaded. We're adding more and more sensors to the system. What you see is an example of an online transformer monitor where we can bring the oil from inside the main tank of the transformer through this sensor, and it can detect up to 8 different gases dissolved in the oil. And the presence of any one of those gases is a specific failure mode that's occurring in the transformer. Then the concept of a separate control system for the distribution part of the grid we call distribution management system, or a DMS. And then to the right of distribution management is distribution automation. So here we're putting logic downstream of the substation. And here's where we do an application such as fault detection, isolation, and service restoration. A fault occurs on the distribution system. We can automatically detect it, isolate it, restore service upstream and downstream. If we distribute the intelligence, as I talked about before, and close the loop on the logic. And then smart metering we'll talk about with respect to the information that meters can provide to us in addition to just the meter readings themselves. Okay? So I mentioned about residential rooftop solar PV. So I wrote an article in Power Electronics magazine, the August 22nd, 2013 issue, and it was after looking at the results that were experienced both in California and Arizona, where a distribution feeder had 35% penetration of the homes on that feeder had rooftop solar panels, and the impact that cloud and fog have on the distribution grid. So as an example, San Diego Gas and Electric, one of their feeders, the homes along the ocean had fog that blocked the sun's rays in the morning, and as that fog burned off, go from 0% to 100% sun, and the voltage on the feeder would spike and then oscillate as the cloud cover went in and out. And so 3 impacts of that, and basically what these are new applications for power electronics. First one is the online tap changer with the substation transformer. So the tap changer has 32 tap positions. It automatically changes tap positions to keep the secondary voltage constant as the primary voltage changes. In this one substation, it's SDG&E, it would normally operate maybe 5 times a day. Now with 35% penetration of rooftop solar PV on that feeder, it was operating 90 to 100 times per day, which with a mechanical device, its lifetime was shortened from projected to be over 30 years to well less than 5 years. So number of suppliers like GE have a new power electronics-based tap changer, because the future with more volatile grid, we have to rethink ways to control the grid that don't have mechanical means of control that just wear out too quickly with the intermittency. Second is low voltage network dynamic grid edge controllers, power electronics-based controllers that we actually install on the low voltage network near the residence. And then third is smart inverters, what we call increased capability from inverters. So I mentioned about policy. Policy was passed in the state of Queensland in Australia that incentivized residential customers to get rooftop solar panels. That happened, and very quickly actually, and the 2 utilities there weren't prepared for how quickly it happened and the increased volatility to their distribution system. But this article that was written in November, December of last year in Intelligent Utility magazine talked about when residential customers have their own generation and get the feeling that they're self-sufficient and don't need the utility, and possibly say, I don't need the utility, I'm going to be on my own. And they stop being a customer of the utility,